So let's look at the big O and log n sorts. So this means we're going to look at how we're going to implement algorithms for sorting and keep, as always, the worst case as n log n instead of n square that we get from section sort, bubble sort, and insertion sorts. One we call merge sort. So note that in n square is very big, right? It's a lot larger than half n square, right? Now if we have half n square plus half n square, right? So this could be 2 to the 4th n square and plus 2 to the 4th n square. So that's going to give you the result of half n square because the common factor is 1/2. So we think about if we can look at our array and we cut it in half and we sort each segment and then merge the two back together, we should end up sorting entire array with a lot less work, right? So for example, this is an array that we want to sort the size of 100, 0 to 99. So if we do bubble sort, selection sort, insertion sort, it's going to cost n square about 100 square, 10,000. That's the worst case. Now, how about we cut this in half? So we have half n, 50 and 50. So we look at, this is math, right? It should reduce our time, right, to 50 square plus 50 square. Just like that, 100 square, right? And 50 square is 2,500 plus 2,500, that's 5,000. And we plus the algorithm to merge. It's cost about its size of it, which is 100. So this should reduce in half. Instead of 10,000, reduce to 5,100. And if we keep doing the same again with the 50, 25, and 25, and 12 and a half, 12 and a half, and 6 and 6, and 3 and 3, so it should reduce a lot because we cut in half all the time. This is like log n, right? And do n to merge, so it's n log n. So we say merge sort will give you n log n. Cut the array in half, that's the algorithm, right? Cut in half, sort the left half, and sort the right half. But do merge sort again, right? Merge the two sorted half into one sorted array. So merge sort itself a sorting algorithm. We might as well use it to sort the two other halves, like I said, right? We can make merge sort a recursive method and let it call itself to sort each of the two subarrays. So we can implement using recursive. Cut the array in half, merge sort the left half, merge sort the right half, and merge the two sorted halves into one sorted array. So let's look at the method. We pass first and last index. And last minus first plus 1, right? That's the size. And best case, if size less than 2, do nothing. Because it doesn't have to sort anymore. But array, and in general case, it's cut the array in half, merge sort the left, merge sort the right, and merge the sorted half into one sorted array. So let's look at, we have array 1 and array 2. We want to look at how we're going to merge. We already know we can cut in half, right? So how do we merge these two? To merge, we compare the index 0 of array 1 to index 0 of array 2. The values 1 and 2. We see if it's less than, alright, if it's less than, then we move from array 1 to final array. So we move 1 to final array because it's less than. And we keep doing that again. Compare array 1 to array 2. We see that now 2 is less than, then move from array 2 to final array. So we have 3 arrays, right? And we keep doing comparisons like that. So that's why it's called linear in, right? To merge unto the end, so we get a sorted array. Keep comparing the values from each array and put the lower one to the final array until there's no more to compare, right? Like last one, 6 less than 7, move from array 2 to final array. And we see that array 2 is finished, so we just move the remainder of array 1 to final array. Don't need to compare anymore. So if you look at the actual merge problem here, the values left first, left last, right first, right last. So that's left part and right part. That itself also keeps sorted, and then we just merge. Right, when we merge, we just create a look at first left, and this is your temp, and move. Right, that's how we move, and then we get a final array, which is sorted array. So this is the merge algorithm. Merge, take the left first, left last, and right first, right last, those index in, and start index to left first, while more elements in left half and more elements in right half. We just do iterating of the merge by comparing the left first to right first. If less than, set the temp array, which is the final array, to the values of the left first. Otherwise, set right, and then we increment left first, right? Else, set the temp array index to values of the right first, and then increment the right first. And then we increment index of the array, temp array. We just keep doing that. Let's start to finish the merge, because we wish no more elements in left and no more elements in right. Then copy the remaining elements from left to temp, or copy the remaining elements from right to temp, and then we get the final, which is copy the sorted elements from temp back to the values. Then that's the sorted, right? The values of the array of unsorted. The code for merge, okay, so use Java to implement, right? Now, you see when you analyze the MergeSort, if we have a size of 16, we split in half and half, 8 and 8, 4 and 4, 2 and 2, and 1 and 1. So this is like only 4 levels that we do sort, right, and merge. Level of merging. So this is like the efficiency is going to come to right? Log 16 base 2 is giving you 4. So the efficiency of it's going to be log n. This is 16 as the n. We only do 4 times, right? 4 levels. The total work needed to divide the array in half over and over again until we reach a subarray of size 1 is big O of n. So it's take O(n) total step to perform merging at each level of merging. So the number of levels of merging is equal to the number of times we can split the original array in half. So if the original array is size n, we have log n levels. We've seen it in the previous image. So this is same as an analysis of the MergeSort algorithm in section 6.6, the BST. Because we have log n levels and we require n step O(n), right, at each level, the cost of the merge operation is going to be big O of n log n. Because of the splitting phase was only n, we conclude that MergeSort algorithm is big O of n log n. Now comparing, if you do n squared like selection sort, bubble sort, insertion sort, to MergeSort and log n, when we have 32 elements, if you do n squared, it's going to cost you 1024, and log n is going to cost you only 160. Okay, if we have elements like 64, cost you 4096, and log n only 384, and so on up to, if you have 4096 n, like when n is large, bubble sort, insertion sort, selection sort are no longer efficient. It costs 16 millions, about 17 millions time, right? But and log n only costs 49,000 times. But this is the worst case, right? So in log n should be better. Now drawback of MergeSort. It's required an auxiliary array that is as large as the original array to be sorted, so its space is not good because we need more space. If the array is large and space is a critical factor, so this sort may not be an appropriate choice. So we can look at 2 other sorting techniques that also give you n log n. It's going to move the elements around in the original array and you don't need an auxiliary array. We don't have to create a temp array anymore, which we call quick sort.